All right, so you want to go over electron dot notation, right? Okay. So electronic devices during instruction is supposed to be turned off. And we want to go over electron dot notation. Did you pick an element? Magnesium? Okay, so we want to do it at magnesium. Now, since you picked that one, let me just reiterate the fact that magnesium sounds a lot like manganese. So you need to be very careful when you see magnesium or manganese that you have the right element. Okay? There are a number of those that are like that, but that one probably gets mixed up more than any other element that I know of in the stuff that we do in here. But magnesium is element number 12. And so to get the electron dot notation, I want to start with orbital notation first, because that's how we learn to do that. Okay? So starting with the orbital notation, magnesium is here in the third row of the periodic table. And so that means that it represents the placement of magnesium here on the third row represents the placement of electrons in the third primary energy level. And when you start putting electrons in the third primary energy level, it means both 1 and 2 are completely full. Okay, so what we need is a full first energy level represented by the elements in row 1 and a full second level represented by the elements in row 2. And so hydrogen is here, so that would be 1, and these first two columns are the S sublevel region, so we're putting electrons in 1s. Helium over here really belongs here when we're talking about the S, P, D, and F sublevel regions. So we're putting electrons in 1s when we put electrons in there representing the placement of hydrogen and helium. And we do that like this. Here's 1 is the primary energy level, S is the sublevel. Orbitals are represented by boxes. S sublevels only have one orbital. And the two electrons, one for hydrogen and the one for helium, look like that. An upspin and a downspin, representing the way that electrons behave so that they cancel their electromagnetic repulsion, allowing you to get two electrons in the same orbital. So that's the first level. That's done. So we get to the second row of the periodic table here with lithium. So now we go to 2. The second row is the second period on the periodic table. And elements there represent the placement of electrons in the second primary energy level. So we start out going through the S sublevel region right here. These first two columns represent that S sublevel region. So these are 2 S electrons, 1 orbital in an S sublevel, and 1 electron for lithium, 1 for beryllium, 1 up and 1 down. Once we get to past beryllium, we go over here to the P sublevel region. All of these columns, save for helium here, all of these columns of elements represent the placement of electrons in the P sublevel region. So we're still in the second row of the periodic table. That corresponds to putting electrons in the second primary energy level of the element of the atom. So that's 2p. That's the sublevel region P. Second row is second primary level, P sublevel region P, and P sublevels have 3 orbitals, 1, 2, and 3. Now, since we're going to completely fill this up, we need 1, 2, 3, 4, 5, 6 electrons. And you start by putting 1 in each box, and then if you need more electrons, then you pair them up until you get to the number you need. In this case, all 6 of them will be full. Now we get down here to the third row, and that's where magnesium is located, in 3 in the third row, and the S sublevel region. So we need 2 electrons, 1 for the placement for location of sodium, 1 for magnesium. So here's 3. This is the S sublevel region, S. 1 box for S, 1 up arrow, 1 down arrow. So that's the electron dot notation for magnesium. That's the orbital notation for magnesium. From that, we're going to get the electron dot notation. And so this is orbital notation. Then the electron dot notation is kind of a condensation of that. We kind of shrink it down a little bit, don't put as much information in there. We write 1s, and we count the electrons in that sublevel. That becomes a superscript, not a subscript now, a superscript. So 1 is a coefficient, s is lowercase, has to be basically half the size of this number, and the superscript is, well, you know what a superscript is, okay? And then 2s and 2p, 1, 2, 4, 6 electrons in 2p, 3s, and 2 electrons in 3s. So that's the complete electron dot notation. I'm sorry, not the electron configuration. And we could also, while we're here on the subject, we can do the shorter version of that called the noble gas electron configuration. All we got to do is go back to the next lowest noble gas. That would be neon. And neon's orbital notation ends right here with 2p6. So we can replace all of this, 1s2, 2s2, 2p6, with the symbol for neon. Okay, but it has to be in a bracket after the colon. And we have 3s2, and that's all that you need for the shorthand or noble gas electron configuration. One of the benefits, one of the disadvantages is you don't see what we left out. We don't see what's left out even when we go from orbital notation to electron configuration. There's less information here. But one of the benefits of doing it this way is you can see what exactly are the valence electrons. So in noble gas electron configuration, we're only showing the valence electrons here. Well, that's all we're going to show in the electron dot notation, for that matter. Okay? So for magnesium, there are only 2 electrons in the valence level. So you need to know what the valence level is. The valence level is whatever the highest primary energy level is in the electron. So these big coefficient numbers tell you what the primary energy level is where those electrons are located. So right now, you only have an S sublevel. You could have a P sublevel, but magnesium only has an S sublevel in the primary energy level that's highest, and that's what we call the valence energy level. Okay? So the valence level is the level highest in energy, or the highest primary energy level. And all the electrons in that highest energy level are valence electrons. Okay? So for magnesium, we only have 2 electrons in the highest level. You can see it here in orbital notation. You can see it here in the complete electron configuration. You can see it here in the noble gas electron configuration. So if we only need 2 electrons, the rule about electron dot notation is we're going to put 1 dot on each of 4 sides. We imagine there's a square around this. Don't actually write a square, just imagine it. And put as many dots as you need. And you stop when you finish. We only need 2. 1 on each of the 4 sides. So you could put them here and here. Or here and here. Or here and here. Or here and here, and so forth. You know, you can keep on figuring out other ways to do it, maybe. Okay? All of those are perfectly acceptable. 1 on each of the 4 sides, and then if you need to pair up, you go back and pair up. But remember, you can only put 2 electrons on each of the 4 sides. So when you get 8, you've got a full valence level. You can't go past 8. At least not at this point in time. When we get to bonding, there are times when you can do that. I'm not sure we're going to cover that in CP chemistry class. Okay? Any questions? All right.